Hi, this is Math 2115, Remote Delivery. For April 30th, 2020, this is a content lecture, and we're covering digital logic circuits and Boolean algebras today. And when you see this symbol, you know what to do. And I'd like to start out with something that maybe is encouraging, and so I'm taking this from well, it's the Lord of the Rings series, but this is from The Hobbit. And Tolkien said, "So comes snow after fire, and even dragons have their endings." So, for us, one day, these days, the area of COVID-19 will be a memory for us. We can make this a legacy of accomplishment. Our shared opportunity is to strive, to teach and learn, to earn our grades, and continue our educational pursuits unabated, in spite of the challenges. Finish strong. That is what champions do. That is what I hope all of you are able to do. A big idea in this lecture is that the Boolean algebra, the logic stuff that we've studied before, actually has a very significant application into circuit design, and for every circuit, there's a Boolean algebra representation, and for every Boolean algebra representation there is a circuit design. And they call this Boolean because once upon a time there was a fellow who did a lot of work in logic, and his name was George Boole. Fast forward a bit, this is often considered the father of information theory. His name is Claude Shannon. He was a strange fellow. He worked at Bell Laboratories, and the legends that I heard of him at Bell Laboratories was he would show up, and during the early lunch he would play chess, and during the middle lunch he would play chess, and during the end lunch he would play chess, often with several players at once. But then he worked all night, and when he needed to stretch his legs, he rode a unicycle that he designed all the way through the Bell Laboratories. He also was an expert juggler. And once he was at a conference, and the coordinator of the conference saw him and said, "Oh my gosh, we have a legend here at our conference. Claude Shannon, would you like to say a few words with us?" And Claude Shannon pulled several balls out of his pocket and just started juggling. That was his performance. Quite a character, but quite an innovator, the father of information theory. And he observed that, gee, if you have a circuit that is open or a circuit that's closed, here no current will pass through, here the current will pass through, and it'll make a light bulb either light up or not light up based on how it is. And these switches could be in series like this, and they could be in parallel. Now here, both of them have to be true to light the light bulb, and here either path will work, so one of them, and you can start thinking about, oh, just this like conjunction, and this is like disjunction that we studied earlier. And in fact, we can look at this sort of like truth tables, where for the switches are in series. For the light to be on, they both have to be closed, and otherwise the light is off. For switches in parallel, the only time it will be off is if they're both open. Now, more complicated circuits correspond to more complicated logical design, and this correspondence exists between the Boolean algebras and the circuits has been studied for a long, long time. Now, in the 40s and 50s, the switches were replaced by electronic devices, with physical states of closed and open correspond to electrical states such as high and low voltages. And in fact, these were called transistors, which are also invented at Bell Laboratories. And the people who invented this were physicists, they were scientists, and Bell Labs used to have a lot of scientists, as well as electrical engineers and many different people. So Bardeen, Brattain, and Shockley were the inventors of this. Shockley was the manager, and his team had been trying to develop a new kind of amplifier for the telephone system. But what they actually invented turned out to be much more widespread. Now these two guys working together, they worked for Shockley, made the first practical transistor, and that was a point contact transistor on this date in history, kind of a famous day. Although Shockley had planned to play a large part in the project, he was furious and agitated about being left out. And shortly thereafter, during a stay at a hotel during a physics conference, he single-handedly figured out the theory of the junction transistor, a much better device than the one they had come up with. Eventually, Bardeen quit Bell Labs, and he studied superconductors at the University of Illinois. Kind of an interesting path. Bardeen stayed there for a while before he also became a teacher. And Shockley set up his own transistor-making company and helped to inspire the modern-day phenomenon that is Silicon Valley. The physics they were doing was the physics of the element of silicon. That is why it's called Silicon Valley. And this is the prosperous area around Palo Alto, California, where many electronic corporations have congregated and where Apple Computer and many other Hewlett-Packard, so on and so forth, have arisen. Now, two of his employees, this is Shockley's employees, Noyce and Gordon Moore, went on to found their own companies, which eventually became Intel, the largest chip maker in the world. Now, what they made for a transistor, and we could spend an entire class talking about this, but it can work as an amplifier, it can work as a switch, and we're mostly talking about how it works as a switch, although this is what they eventually were working on. Gordon Moore from Intel also observed, and this is, by the way, when I grew up, I actually had a radio, and we called it a transistor radio, and this is much what my radio actually looked like. I used an earphone, and I listened to baseball games on the radio. I still prefer listening to baseball games than watching them, listening to them on the radio. Anyway, Moore at Intel developed an observation that the number of transistors in a dense integrated circuit doubles every 2 years. And this is a very famous thing, and when you think about that, that makes things be cheaper and cheaper and faster. But, and here's an example of one of the first ones, and now modern microprocessors consist of several CPUs on one chip, which is about the size of a fingernail, and will contain close to a million transistors and several hundred million logic circuits, and hundreds of millions of instructions per second. Actually, this is a little bit out of date. They're even stronger than that. But this is what the first one that they were talking about, the Intel 4004 chip, looked like. Now, Moore's observation has been true in very large-scale integration for a long time. But it does not state that you're going to introduce that technology mode every time, and it does not suggest that the computation power will increase just because you did that, or the clock speed, or even the power consumption will be lower. But the story of runaway progress in silicon can't continue forever. We're reaching the end of this amazing technology explosion. There's some people say there are perhaps 2 or 3 more nodes. We're running out of ways to make computers faster. You can only make transistors so small because you run out of room. And for example, here's another chip being referenced. This is one of the best as of the writing here. We have today had this many billion transistors in an area that is very small. Going much smaller than this, the transistors become so tiny that the effects of quantum physics start to interfere. Electrons start to jump around and turn up in places you don't want them to be. With so little space, it becomes difficult to organize the structure of the wafer that's essential to control its electrical properties. If you pack too many transistors and make them work faster, the restricted flow within chip can make it so hot that without significant cooling it will burn up. Lots of problems at the end of this technology. You will see it. There are many ways that people are trying to address this, parallel processing and other clever things, but perhaps the most familiar is to supersede conventional silicon chips in quantum computing, and instead of letting quantum effects prevent our tiny transistors from working, build devices that take advantage of the quantum effects that do make them work. So rather than using bits, and we'll talk a little bit about that, but that's what is the basic unit of information, and it either has this value of 0, 1, you can think in a different way about a quantum state where you have a north and south pole. You think of those as being 0, 1 on a sphere, but a qubit, standing for a quantum bit, can take any value on the whole surface of the sphere. This allows them to process more information with less energy. There are tons of research happening with big folks, and one day I think what you will see is quantum computing will in fact be a reality. Looking back a little bit, this is a picture of John Tukey, who was the one who came up with the idea of using zeros and ones and rather than trues and falses and storing things that way, and he called them zeros and one for binary digits, and he was a statistician, but back in the day there was not a whole lot of difference between applied mathematicians and engineers. In fact, there still is not. If you can do math, you can do anything. Okay, so let's continue with our discussion then. So the idea is you want to design a black box which takes a certain amount of inputs and gives you a certain output symbol. And so here, associated with this black box, we have a input which could be ones or zeros, and you have an output that could be ones and zeros. But this black box performs according to this input-output table. So you see, if you get 3 highs or 3 ones, you will get a 1. If you get a 1 in P, you will get a 1, and you'll get zeros, and so on and so forth. So you see, this input-output table completely defines the functioning of this black box. And we define certain kinds of gates that will be combined to make the circuit. It's a gate because there's an input and there's an output, and sometimes there are more than one input and more than one output. Here we talk about a NOT gate that's represented by this, and the NOT gate is a triangle with a little circle on the end of it, and this is how it acts. This is an AND gate. The inputs are P and Q, and it looks like that, and the output is R, and this is how it performs. Now this is just like negation. This is just like conjunction, and this gate designed in the circuit is OR, and that's like disjunction. There are rules for combining things into a circuit. Never combine 2 input wires. They get combined at the gate. A single input wire can be split part way and used as an input for separate gates. An output wire can be used as an input into another gate, but no output of a gate can eventually feed back into the gate. Now we relax this last constraint later when we talk about sequential circuits, and we're running a little bit out of time, but I think I will make it a point to talk about sequential circuits. And so the output can cycle back, and so the output at any time depends both on the input at the time and also on previous inputs that were given. Now this is a good part for us to probably break. What I'm going to ask you to do is look at these 2 gates, and these are circuits, and we have the ands and ors and nots and so on and so forth, and we have these input signals. So what I'm going to ask you to do is pause and work this problem, and when I come back for the next part, we will pick it up from here. I will see you in part 2.